Good afternoon, everyone. I'm Helen Rosenfeld. I'm the Executive Director with MSEF, the Massachusetts Science and Engineering Fair. So excited to have you guys join us this afternoon for our speaker series. We started doing this as a way to connect you with academic and industry experts in a variety of STEM fields. And so I'm excited to introduce you today to Mo Steinman, who will share about his background and the work he does. So thanks for joining us today, Mo, and I will hand over the platform to you. And just, one note to everybody. I welcome you to take yourselves off video if you'd like to kind of connect as a group. And as we go, if you have questions, feel free to put them in the chat. I will then later, as we go, facilitate the questions and perhaps take you off mute and invite you to ask your question yourself. So thanks so much.
All right, thank you, Helen. All right, let me, oh, hey, Helen, could you enable screen sharing? It doesn't allow me to do that.
Yes, sorry. There you go.
Beautiful. Okay, thank you. All right, so let me get my presentation going here. Move my little thing out of the way. All right, can everyone see, does that look
perfect?
Visible? Okay. All right. So as Helen mentioned, my name is Mo Steinman. My real name is Maurice, but nobody calls me that. Professionally, I've been known as Mo throughout my entire career. I'm a computer hardware engineer, and currently I'm the vice president of engineering at a small company, a small startup called Lightelligence. What I plan to go through today, so I'm going to start off with my career path, kind of like a timeline, starting from high school all the way to today. And because my career is very long, that timeline is very long, but I promise to not get too bogged down in it, and we'll try to go through it pretty quickly. I'll try to point out some of the, I would say, the key inflection points and decision points in my career, and just kind of think of it from a highlights perspective. But at least just going through the whole thing, you'll kind of see the road that I've taken to today. And then I thought I would talk a little bit about the day-to-day activities of a computer engineer, specifically a computer hardware engineer. Certainly not, the complete list of tasks that, happen during, an entire year or project, but just kind of talk about it a little bit at high level. And then I thought I would share a few random comments, right? Some observations I've made over the years, some notes, maybe a few recommendations. And then we'll leave it for questions and answers at the end. All right, so let's talk a little bit about the career path, specifically the beginning, all the way back to the late 1970s when I was in 10th grade in high school. And my first exposure to computing was actually in my 10th grade math class. We had a unit on computer programming in basic language, which was very popular beginner language back then. I'm not even sure if it's still relevant today, but it's a very simple programming language, and I was absolutely fascinated by it. And it was pretty archaic computing platform, relative to today's standards. We actually would connect to this large remote computer using this, teletype thing that's down at the bottom of the screen there, and connected through the telephone. Very primitive, but it was exciting, and it really kind of sparked my interest. And then my mom bought me a personal computer, and that's what a personal computer looked like about 40 years ago. Sort of resembles a personal computer today, but with keyboard and a screen, but a little bit more clunky. And that allowed me to kind of do a little bit more on my own at home. And after doing that for, I would say, a couple of years, I think I reached sort of a saturation point. I really kind of enjoyed interacting with computers, programming them, doing things with them, playing games, even primitive communications that we could do back then with them, like chat. But I really wanted to know what made them tick. I was fascinated by what it would take to actually design a computer, and I started looking into that, and I decided that's what I wanted to do as my career. So I knew, I would say probably junior year of high school that is what I wanted to do, and that was with I would say with laser focus. I just absolutely wanted to get into that. I went to enrolled in and went to RPI, Rensselaer Polytechnic Institute, which is in upstate New York, and I graduated with a degree in computer and systems engineering in 1986. So with that degree, that was what enabled me to kind of start my professional career, which we'll talk about here. So the first few years in my career, I started working at a company called Digital Equipment Corporation, which was at one time the second largest computer company in the world. It no longer exists, but it was second only to IBM. It had a very large New England presence, probably 50 to 70,000 employees just in the Massachusetts, New Hampshire, Vermont, Maine area. Very, very strong New England base. The company was founded by some people from MIT back in 1958. I joined on in 1986, and my first job was as a CPU design engineer, which was just an incredible learning experience. And the first project that I worked on actually lasted 5 years. It finally went to production. It didn't sell very well, unfortunately. It was not a commercial success, but completely selfishly speaking, it was an amazing learning experience for me to just be immersed in the full product design cycle on a real state-of-the-art design. I was very fortunate to have that as my first job out of school, and I think it was really a very good foundation for the rest of my career. Further cemented that what I originally had sort of dreamed of doing back in high school. Incidentally, the computers that we used in high school were manufactured by Digital Equipment Corporation. So I got an opportunity to actually work on the inside at that company. And then for the next 7 or 8 years, I had several different roles at Digital. Digital is a very big company. It had many buildings, and there were many, many projects that were going on at any given time. So it was possible to sort of move around within the company and almost have what is like a major job change without actually changing, the company that you're working for. And so, in 1994, so after about eight years on the job, I started actually having my first management role. So I took over running a small team of about 5 engineers. I was also somewhat of an individual contributor and manager, so I contributed to the design, but I also ran the team. That was my first experience in management. Later, I joined a different part of Digital, working on alpha microprocessors, which at the time were the highest performance processors that were available in the industry. So that was another great opportunity to be working there. And then, from 98 to 2003 was kind of an interesting little journey. Digital, the company that I'd worked for since I joined, since I left school in '86, was acquired by another company, which was called Compaq. And then that Compaq was bought by Hewlett Packard. So, within a few years, I kept finding, my beloved company changing names, new business cards, new sign on the outside, but the work sort of stayed the same. It was really kind of really a change in name only. Towards the end of that period, by 2003, the group that I was in was sold to Intel, so that was that's a big company I'm sure everyone has heard of. But during those 5 years, it was a lot of changes going on. But it was interesting because it was an opportunity to see different perspectives, different corporate philosophies, and operating models. So even though it wasn't by choice, I would say I benefited from getting to see more perspectives than I would have had I stayed at one company. Well, and then the next phase, I would say from 2004 up to 2018, I had left Intel to work for Advanced Micro Devices, AMD, also still in the Massachusetts area in Boxborough. I was fairly unhappy at Intel, actually. It was a it was a corporate culture that I wasn't accustomed to. It was a bit of a change and from what I was really comfortable with, and I decided to to look elsewhere. And because of during those first I guess 18 years of my career, I really changed jobs really either through internal transfers or the company changing names. So this was the first time I had done an outside interview in a really long time, and I was very rusty and hadn't kept my resume up to date. So I would strongly recommend that once you enter professional life, to always keep your resume fresh. It doesn't mean that you're disloyal and looking for looking to jump ship and change jobs, but you never know when that opportunity is going to come up, and it is better to have your resume ready rather than to hurry and put something together. But I was very happy at AMD. I stayed there for 14 years, and I would say my career really propelled there. I had increasing levels of responsibility and visibility within the company and the industry, for that matter. And I reached the title of senior fellow, which was the second highest engineering title that AMD has. So I had a really good opportunity there. It was a great company, and had a really good I would say career growth opportunity and personal growth opportunity there. And then about a year and a half ago, I left AMD. I was happy there, but I had the opportunity to join Lightelligence, which is an early stage startup in artificial intelligence. There was a small team of founders that were looking to hire an industry veteran who had kind of been through the ropes and made all the mistakes and could help navigate, a new company through some of the, the difficult parts of engineering. So for me, it was really exciting to kind of jump out of the corporate mold. AMD was the smallest company I had worked for up to that point, and that was 10,000 people, right? So now I joined a company with 10 people, and that included me. It was a big change, but it was a very exciting way to sort of reinvigorate my career. And in terms of responsibility, there isn't a big corporate infrastructure behind you, and it's a new exciting field of artificial intelligence, and an opportunity to work on new technology with a very vibrant and energetic team. So that's sort of the career path, how I got to where I am today. 32 years rolled up in a few slides. But I've been very fortunate to have a very interesting career and to have worked for some really great companies. So let's switch gears a little bit and talk about, I'm going to see if I can get rid of this thing here. There we go. Talk a little bit about the day-to-day activities of a computer hardware engineer. And by no means is this complete, but I just thought it might be interesting exposure to how it's done. In a lot of ways, things haven't really changed too much in terms of the design philosophy and approach, but the degrees of automation and sophistication and the tools that we use to do the design have improved quite a bit. But I will say that computer engineers make really extensive use of electronic design automation, or EDA as we call it, tools. Gone are the days where people would draw these large almost like blueprints or layouts of schematics by hand. It's really done with a lot of computer automation, and so the EDA tools are really just a package of software that allows us to enter the design, and it's really a representation of the chip design. And then it allows us to model it, to simulate it, and analyze its behavior before we release it to manufacture. And really what we want to do is find all the things that are wrong with it and make sure that it operates in the way that we expect it will if we go to manufacture it. And the reason why this is so important is that a state-of-the-art chip can cost tens of millions of dollars to manufacture. So before a company is willing to spend that kind of money, We really want to go through and make sure we've simulated every conceivable operation that a computer can do, and we do that with simulation and modeling, and we do that using the EDA tools. So that's a very powerful, suite of software that we do to make sure we design, capture the design and find all the issues with it before we send it off to be built. Computer hardware engineers often write code themselves, and it sort of looks like software, even though we're hardware engineers. And we use computer languages that are called HDLs, or hardware description languages, right? So we'll use that to enter the design into the EDA system. And generally hardware engineers that work in sort of the logical domain or thinking about the operation of the computer will express their design using this kind of software. But it's important that you have to have a strong foundation of hardware to understand the hardware that the software represents. I know that's a little confusing, but it is not something that necessarily someone that's trained as a software engineer will have the skills to do. You really need to have the hardware engineering background. Some designers still will draw circuit schematics with electronic symbols for things like transistors and resistors instead of code. It all depends on what part of the design you're actually working on. So, the EDA tools, they help the engineer convert these code or schematics into a format that the chip factories, which are called foundries, can actually use to manufacture the chip. And so we actually, when we've completed the design and simulation and modeling of a chip in the EDA tools, we compile all that information into a single file. It's a large file, and we send that file to the foundry, and they use that file to build the chip. But it is important. Like I said, it's important to understand the hardware concepts, even if you're writing code to represent the hardware design. And as I mentioned, it's important to find all the mistakes in the design. So that process is called verification, and that is a whole field within computer engineering, design verification. And really, their job is to find all of the bugs or mistakes in the design using simulation and modeling. And bugs can take many, different shapes. They could be logical issues. They could be sort of like an if-then-else equation that is incomplete or incorrect. It could be an electrical issue where the electrical circuit doesn't, match expectations in terms of speed or power or other electrical characteristics. Or it even could be something related to the reliability or even the manufacturability of a design. It's possible we could design something that is difficult to manufacture, and it's important to identify those things ahead of time. So we try to get all of those things out because of the tens of millions of dollars that it could cost to actually manufacture it. And a very complex chip like a microprocessor, takes several years from start to finish. So it is definitely a marathon operation. A little bit of a historical perspective. When I first started out back in the mid '80s, just about all of my colleagues, at Digital, were working. We all worked in the same building, even the same floor, and that made collaboration very easy because it was as simple as just sort of dropping by someone's cubicle and scribbling on their whiteboard or having a chat with them. As with many companies, but particularly technology companies, they're multinational, or nearly all of them are. And it's very likely that your colleagues, perhaps even on your same project, could be all over the world. I can remember times when I was at AMD where I would be on a conference call talking to people in Texas, California, Canada, India, China, Germany, all at the same time, which means that somebody is doing it in the middle of the night because there's really very little. There really is no time zone that works for all geographies at the same time. But because of this, model, and this is really a reality for tech companies today, that they are multinational. Collaboration today puts, I would say, a much greater requirement on your ability to communicate clearly and effectively. So it's very important to have good presentation skills, good speaking skills, being able to share your ideas, share your assumptions with your colleagues, because it is not as effective as a face-to-face communication if you have to use something like we're doing right now through Zoom or another tool. I would say the burden on communication is a little higher today than it was when I first started. Working at large companies, I've mostly worked at large companies before I've joined my small startup that I'm at now. But working at a large company can certainly have its advantages as well as disadvantages. On the disadvantage side, they can be somewhat to very bureaucratic, because big companies with tens of thousands of people. In order to manage a company that large, you have to have several layers of hierarchy in the management. It's not a question of one or two managers and everybody works directly for that. That's not really scalable to an organization that large. So as soon as you start inserting layers of management, it means that the decision-making process takes longer. More people have to be involved. Sometimes the communication gets impacted, and the message changes from the time it began to the end. So it's it can be a little bit bureaucratic in order to make sure all of those communication inefficiencies are reconciled. But I would say one advantage, and I took full advantage of this, as I mentioned before, is you can actually seek a lot of new roles without changing company. So it's a bit of a trade-off. You have that advantage, but some people may be frustrated by the big company bureaucracy. One thing I will say, regardless of the size of company, I would recommend that you seek roles. If you're interested in an engineering career or a STEM career, and maybe this is generic advice for any career, but I think it's important to seek roles that make you a little bit uncomfortable. And what I mean by that is, it should not be something that is very easy to do, and something that's not going to stretch your abilities or cause you to have to learn new skills. I like the idea of trying to be a little bit uncomfortable as a way to propel growth. The other sort of thing that goes with that is it's important to have a supportive organization, right? So to be able to find a company that's willing to let you find those uncomfortable roles and stretch yourself, and values that that sort of risk taking or ability to kind of have some career growth on the job. I think that's very valuable, and I've definitely benefited from that. Another thing that and this is fairly specific to computer engineering, but it may have some analogies to other types of jobs, is as a computer engineer, the parts of the computer system that I worked on were more, I would say, the external parts, or the system-y parts, as we call them, as opposed to working on functionality is very, very deeply embedded in a chip. I tended to get involved in the things that were more at the external interfaces of the chip. This was just sort of a personal preference, but that gave me a few opportunities that I think may not have come my way otherwise, because I was involved with the more external parts of the computer, and not very much the very deep inner part. It meant by necessity I needed to collaborate with people from a lot of different disciplines, including software, even customer service and sales and marketing. And so I really enjoyed that, because it was an opportunity to kind of see outside of my narrow scope of what I was working on, and I think having an understanding of how your design is used in either business or software contexts, I think makes you a better design engineer. So I really enjoyed that. And then as far as the career advancement perspective, because I was interacting with so many different teams and different people, it gave me additional visibility within the company, and those are things that help with promotions and career development. So I thought that was something that I found myself enjoying, and I was fortunate to be in this part of the design. A word of caution, and I don't like to talk about this very often, but when I was a junior, senior in high school, maybe I didn't get the appropriate guidance I should have from guidance department or my family, but I only applied to two colleges, and I was accepted at one of them, and that was Rensselaer Polytechnic, RPI. And I have no complaints. Everything worked out really well. I was very happy with my college experience and how my career took off. But thinking about that in retrospect, that was extremely risky. I was a pretty good student, and I applied to only two schools, two fairly top schools, and I didn't have any other, we'll call them, safer alternatives. So I would definitely recommend not doing that. Maybe that's obvious, but apparently it wasn't obvious to me back then. That's really all I had as far as the prepared material. So I will open it up to questions and answers right now. Ask me anything.
Fantastic. Thank you so much, Maurice. I think I already heard somebody asking a question. So right to you, whomever asked. And you can take your video off as well if you'd like.
So out of all the tech companies you worked in, which was your favorite, or which one did you like working with the most?
That's a great question. If my boss were here, I would have to say that my current company is my favorite company. And in a lot of ways, it still is. But I think if I had to look back in my entire career, maybe there's sort of two that have we'll call it a tie, for different reasons, right? When I first got out of school and I started working on, CPU design, and this was at Digital, there was a little bit of this, wow, I'm actually doing this. I'm an engineer. So there was a definite newness factor to it, and actually, being able to work on something that was going to be a product. So that was all the way at the very beginning. And then that, it was a very fun group. I was young, other people were young. We had a good time. It was a good social experience as well as a professional experience. So for that regard, we'll say that's in one category. As far as what I think was most pivotal and beneficial to my career, I think it was my time at AMD, Advanced Micro Devices. When I left Intel, Intel was a very large company and has a lot of that bureaucracy. Although they are trying to address that now. I know a lot of people are working there now and things are changing. But at the time I was there, I felt it very frustrating. And I also found my scope being a little narrow there. The level of responsibility was more about depth than breadth, which I'm kind of a breadth guy, so I felt a little closed in there. So when I switched to AMD, I found almost immediately I got to be involved in a lot, bigger things, and I had more impact right away. So I would say those two, the very beginning was very exciting because it got off to a good start and it was fun. And I think when I went to AMD, at the time AMD was a struggling company, so I was a little nervous about that. It could have gone under. But in terms of the job scope and responsibility, I learned an awful lot there, and I had a really great time, and was very proud to the accomplishments there. And so that sort of enabled me to get where I am, in my current role.
So we have another question from Dominique. Dominique, if you'd like, you can unmute yourself, or I can read your question. And I think that's a sign. I'll read the question.
Okay.
So it says, amazing presentation. You shared on your timeline a neural network. Can you share anything about your work on AI today and what it entails?
Sure. Okay. So AI is very exciting new field, and it's fairly new for me. While I was at AMD towards the last few years, I got to be a little bit involved with it, sort of at a distance, but not really too closely involved. I had, let's say, I had an awareness of it, and I knew it was a kind of a growing field. Um, and then when people at my current company approached me to come work there, I cautioned them that I don't really have a lot of AI and neural networks background, but I'm excited to learn about it. So what's interesting about AI? There's really sort of two big categories, to kind of oversimplify it a little bit. Uh, and it sort of breaks down into training and inference. So training is where a neural network model will learn from real live data how to recognize an image, make a decision, influence a purchase decision, any of the things that we see AI interacting with it today, like digital assistants, image recognition, self-driving cars. There's an awful lot of data that has to be sort of learned, and it's a fairly compute intensive thing. But in terms of training, the way a lot of these neural networks work is there's a number of parameters that have to be learned, and in a lot of ways, it's just sort of if you give it many answers, or you give it many questions, and along with the answers, you can eventually learn how to develop those parameters to run on the neural network model. So that's the training part. The company that I'm at is actually more focused on the other part, which is inference. And inference is where you use AI to to apply the model and kind of do an AI task. So that's something like image recognition, for instance, being able to recognize characters and or handwritten symbols, or spoken language, or visual input, sensory data like from cameras and radar for self-driving cars. And so the company that I'm at, there's a lot of big companies and small companies that are doing AI inference. The company that I'm at, we're doing it a little differently. We're using photonics instead of electronics. So we actually do computation using beams of light, which is pretty interesting. But at sort of the math level, a lot of what AI inference and even training makes use of matrix multiplication. So if remember that from from math classes, there's an awful lot of vector times a matrix and multiplication in AI workloads, and typically the matrix will hold those learned parameters from training, and the vector will be some representation of the input data. And really, by doing these matrix multiplications, you start to detect different bits of information from the input there. So the long story short is that the company that I'm at now, we're doing that vector matrix multiplication using photonics instead of electronics. But it is a very big field. There's a lot to still be learned and understood about AI. It's very powerful and very exciting. I don't know if I answered the question, but hopefully I covered what you were hoping to get. But if there's any other questions you want to follow up, please do so.
We do have another AI question, but first I'm going to get to, we have a question here from Hamza. Having been a journeyman in the computer world and having seen companies move around, where do you think the computer industry will be in 5 years?
That's another great question. So one of the things that is challenging the computer industry and really all digital electronics now is something called Moore's law. And that law is named after Gordon Moore, who was one of the early pioneers or founders at Intel, who stated that transistor density should double every 18 months. And that's just by evolving manufacturing capability and design capability. So every 18 months, theoretically, we should be able to double the performance of computers. and Moore's law was definitely true to its vision for a long time, but it is starting to slow down. Things that are getting in the way are the feature sizes of the transistors that we build in the most state-of-the-art designs are getting smaller and smaller, and eventually will only be limited by a sort of like atomic dimensions, right? We'll only be able to make transistors that are several or dozens of atoms in size, and we won't be able to continue to shrink or scale those smaller. So that means that the pace at which advancements in performance just on the circuit, performance, how many transistors we can pack into a chip, that's slowing down, and it has been. And so what that's prompting is trying to do different things to kind of get around that. And one of the things that is become a pretty common approach are putting multiple chips together in sort of a chip package. So you're used to, if you've ever opened up your computer and you saw the CPU, there's a heat sink, and it's carried inside like a ceramic package or a plastic package, and usually there's a single chip in there. So one of the innovations was, wow, it's getting hard to cram more and more transistors into one chip, but why don't we just put multiple chips near each other, and that'll give us one dimension of scaling. So that is sort of like two-dimensional scaling. And then the next level of approach that's kind of been done to get around the Moore's law scaling is 3D scaling. So now we're taking chips and stacking them on top of each other. So now you can kind of build them out in an array and also stack them up on top of each other. Stacking up on top of each other creates some challenges because chips do get hot. And when you have multiple chips stacked on top of each other, it does trap the heat there. So there are limitations to how much stacking can be done. After two-dimensional scaling and three-dimensional scaling, we're kind of out of dimensions at that point. I think things will continue to scale. We'll be able to do more aggressive things with 2D and 3D scaling. And the transistor densities will continue to improve, albeit not at the fast pace that they had originally when Moore's law was first done. But it sort of, is the reason why there are people looking at alternative technologies, sort of like what my current company is doing with optical processing. And frankly, that is exactly the reason why I was attracted to it, because I saw this diminishing, performance improvement, coming in the next 5 to 10 years on the electronic side. And I thought something different potentially should be explored, analog computing and optical computing to sort of start a new Moore's law, if you will. And things in the optical domain are still very, very new as far as computation is concerned. They're really only used for telecommunications, fiber optic signals for like, data like, FiOS, internet and telecommunications. But using it for computation, I think is at least my current company is betting on that as the next big thing to sort of open up the scalability again and get back on a faster pace.
Fantastic, thank you. We have another question from Jay Surya, who asked before. I don't know, do you want to unmute yourself or shall I read your question?
You can read my question.
Okay. Are there any types of models in AI that could be implemented in our daily life? How was your first experience when you entered this field or career, this career? Was it pretty challenging at first, or was it running smoothly?
All right, so I'll start with the challenging part first. Yes, it was extremely challenging. There was a lot to learn for me personally. I really didn't know much about AI other than how to spell it, AI. So I did an awful lot of reading when I first started at my new company. There's an awful lot of good literature out there and tutorials. Even just getting comfortable with the vocabulary, because there's a lot of terminology there that I was unfamiliar with. And there's also a great deal more mathematical basis It had been a long time since I had, really sort of stretched my math skills. So it was a bit, bit challenging to relearn that. And then also specifically in the group the company that I'm at, using photonics, there's a lot of physics there, and light was a new medium for me as far as being able to do communications and computation with. So I had an awful lot of learning, and I'm still learning a lot every day. So and the other question was where examples of where AI is being used like every day. Was that it?
Yes,
Right?
daily
Yeah,
life. Yeah.
daily life. So I would say it's probably more prevalent than you realize. If you have a phone that unlocks with your facial ID or fingerprint sensor, that's going to use AI in some respect. Any of the digital assistants like Siri or Alexa or OK Google or Samsung's Bixby, if you interact with those at any time, that's a lot of AI. Self-driving cars are certainly, I would say, one of the most exciting potentials for AI. But even a lot of modern cars today use AI, not necessarily for that ultimate safety and control measure. There's a lot of it in even in the entertainment part of the car. Sort of detecting when to turn the volume up because of ambient noise or things like that. There are some safety things to alert maybe if there's oncoming traffic. There was one other thing I was just going to mention that slipped my mind. Oh yeah, another thing that's very very popular, and perhaps if you've done any online shopping, is something called recommendation. And so that is looking at your purchase history. Perhaps if you've bought something on Amazon.com, you might see them, recommend, different products for you. So that's a combination of looking at what other people have bought and what you have bought, and trying to make a educated guess at what is likely interesting to you and you're likely to purchase. And so recommendation is something that's becoming a very I would say a very fast-growing field of AI, because retailers certainly see the money potential from that. It's very targeted marketing. It also, I think some people are a little unsettled or unnerved by that, but that's that's something that's pretty exciting in terms of being able to like widely deploy AI. Other things that are maybe less out in the forefront in manufacturing flow, being able to identify manufacturing defects. So something that is a very precise device that's being manufactured, and inspecting it with a microscope, using AI models to be able to detect manufacturing defects. It might be able to do that faster or more effectively than a human. Another is in the medical field, and that's a very exciting and promising use in terms of detecting cancers from various signatures, sensor data, or chemical data from a patient, and even to look for treatments for cancer. So I know cancer research is another aspect, and I have to believe that a lot of the coronavirus vaccine research involves AI in some way, being able to help navigate through the trial and error space a little faster with some some intelligent directional choices, maybe from an AI algorithm.
So we're coming up on our 45 minutes, but we do have one more question, is if you're able.
I am able, absolutely.
Fantastic.
Yeah.
Ezra, I don't know if you want to take it off mute or if I should read your question.
I can read it.
Excellent.
Oh yeah, first of all, I have an RPI shirt actually.
All right, cool.
That's cool. My question is basically, you know, in your experience with CPU design, does it often entail building on like prior established design? Is it normally like, you know, taking what you already have as a base and then stacking new stuff on, or are there, I mean, as mentioned with Moore's law pretty much, or are there more people trying to like pioneer original methods?
That's a great question. And from my experience, I've done both. The incremental design is it's a lot easier to think about it and to plan it, right? You're starting with a known entity, and another reality, and I didn't really talk about this, but every project, every major undertaking, by the time you get to release it to manufacturing, um, not everything that you had intended for that design is going to make it to the end. So we're always leaving some things on the table, whether it's some functionality that was hard to get right, had to take it off the feature list and save it for next time. So there's always this queue of kind of a backlog of good ideas that kind of didn't make it from the last one. So those are the easy, obvious things. Well, we'll just get it next time. So those incremental designs are a lot easier to plan and to even to predict. You have a very, very good way to predict the benefit of adding new widgets and features to it. Um, but eventually, those designs, from my experience, they tend to sort of run out of gas. They weren't built necessarily to be scaled with 10 years of horizon in the future, and there's new technologies. So it's often necessary to start with a clean sheet. But one thing that is, I would say, common between a clean sheet design and an incremental design is being able to do very good modeling. And generally, you don't want to, you need to be able to navigate through those good ideas and dismiss the bad ideas early, right? So we tend to kind of go through, I would say, levels of abstraction. You start with a model that sort of represents, the system that you want to do in a very software kind of way, something that can be written quickly, but it also has, maybe pretty high error bar, right? Maybe it's only 80% accurate. But you really need to be able to have some sort of model and be able to run some inputs for it to kind of, get some, test your ideas. You might, an idea might be like, I want to do a computational unit that, can do 10 additions in parallel. Is that worth doing? So maybe I'll write a model of that and I'll run important, common software sequences or benchmarks on it and see if we can exploit those 10, functional units. And if it's worth doing, then maybe, you take it to the next level of more accurate modeling and design. But generally you want to have, I think it's really important to have that architectural model, that high level model where you can kind of evaluate designs when they're still just thoughts. The longer you take, the longer you delay that kind of, evaluation, like if you just assume something's a good idea and then you go build it and, it could be years and hundreds of people, and then you finally evaluate it and it turns out that it wasn't really a good idea. That's dangerous. You really want to, you're better off making early choices that have sort of high error, but at least kind of bias you in the right direction rather than going too long and realize you've made, a mistake that's going to take 2 years to unwind from.
Well, great. Thank you so much to all the students who participated and the fantastic questions. This has been a really active conversation, so thank you. And Mo, thank you so much for your time today and your willingness to dive into your background and what you're working on. We really appreciate it.
It was absolutely my pleasure.
For the students that are on, if you're very interested in continuing the dialogue and there's something that you'd like more information on, if you could email us at info@scifair.com, we can potentially arrange more talks of this nature or specifically with Mo if he's willing. And with that, I'd like to close and just remind everyone that every Tuesday through Thursday, we're having these talks. So there'll be another one tomorrow at 3:30. Hope to see you there.
All right.
Thanks, everyone.
All right. Thank you for giving me the opportunity to talk with you all. I really had a great time. Thank you.
Thanks.
Thank you.
Bye-bye.
Thank you.